everyone. I'm Whitney Espick, CEO of the MIT Alumni Association, and welcome to the October MIT Alumni Forum. Solving for climate change, harnessing the power of AI for good. These are arguably two of the most pressing challenges facing society today, and everyone is searching for the answers on how to tackle each. That is why President Kornbluth has placed them at the summit of MIT's institutional priorities. But, while these seem like two different moonshots, today's speaker will discuss how finding solutions for one can benefit the other and vice versa. Priya Donti, an assistant professor and Silverman Family Career Development Professor of EECS and LIDS at MIT, will be with us today. She is a pioneering research on understanding the impact of machine learning on climate, how we might maximize its positives and better understand how to minimize its negatives. Following her presentation, Priya will be joined in conversation with our moderator, Laura Hesse-Fischer. Given Laura's role as host of MIT's Climate Change podcast, Today I Learned Climate, TIL Climate, I know that we're all in for a great MIT Alumni Forum. And if you already have questions on the topic, don't wait. You can start adding them to the chat box below. Some of you maybe already have. You can also upvote questions to ensure that we can speak to what's on your collective mind. Now I will pitch it over to Priya and just say, enjoy, everyone. Thank you.
Great. Hey, everyone. So excited to be here. And thanks so much to Whitney, MIT Alumni Relations, and Laura for kind of hosting all of this. And today I'm excited to talk about the different ways that AI and climate relate to each other, both the good and the bad. And so why are we having this conversation? I think as Laura already got at in her introduction, climate change warrants rapid action. It's we're already feeling its effects, from storms to droughts to fires to flooding to intense heat. And these impacts are being felt globally with disproportionate effects on the world's most disadvantaged populations. And in order to address climate change, there are two major axes of action. First, we need to kind of reduce the extent to which climate change will occur by reaching net zero emissions by 2050, or more generally, reducing the amount of emissions that we put into the atmosphere. And this requires a rapid transformation across virtually every sector of society, from energy to transport to buildings to agriculture and so forth. In addition, given that we already are experiencing the effects of climate change, we need large-scale efforts to adapt to those effects. And these require kind of actions that are inherently local, in the sense that the effects and the efforts to adapt to those are going to look different in different places, but they have to happen at a global scale. And these kinds of transformations are going to require kind of a rapid mobilization of virtually every tool in our toolkit. And so obviously one question comes to play: where does AI potentially play a role? And so when we think about the relationship between AI and climate change, one thing we observe is that AI is a general purpose, multifaceted tool, which means it has multifaceted interactions with climate action. First of all, AI can be used to actually support climate change related goals. And very kind of present in the kind of modern conversation is the fact that AI itself has impacts that are negative with respect to climate, in terms of the computation it takes, as well as its hardware-related impacts. Often the kind of question of, is AI good or bad for climate change, is framed in terms of these two axes. AI can be used for climate action, but AI has its own impacts. Is it worth it? That said, the conversation is actually broader than that, and I think there are certain aspects that often get omitted from the public debate. In particular, when we think about the ways that AI is applied, it can be applied for good things. It can also be applied for things that are directly counteracting climate action. For example, AI applications that increase emissions, or AI applications that are changing how we consume, how we communicate, how we organize, in ways that also have implications for climate change. So when we think about this relationship between AI and climate, we actually need to recognize that it's much bigger than just good AI applications and direct impacts. And so what I want to do during this talk is actually talk through each of these different axes in a little bit more detail. So the first axis I want to talk about is AI applications for climate action. So where is it that AI can actually play a role in helping us to address this problem? So several years ago, a group of collaborators and I put together this kind of paper called Tackling Climate Change with Machine Learning, which provides an overview and agenda for where exactly AI can play a role. And we found that AI had diverse uses across many different sectors, across electricity, across agriculture, across climate science, in a variety of ways. And while I won't be able to talk through kind of every single application that came forth in that 100-page paper, what I hope to do is provide a little bit of a sense of cross-cutting themes that emerge as we think about where AI plays a role, that hopefully provide a mental model for how it comes in. So a first major theme for where AI is often used is distilling raw data like satellite imagery into actionable insights. For instance, a nonprofit coalition of organizations called Climate Trace, they are using satellite imagery and on-the-ground data in order to come up with independent third-party estimates of where the greenhouse gas emissions are coming from at the entity level, so which particular entities or facilities are actually producing them, and how much, in order to then actually provide a transparent estimate of global greenhouse gas emissions. And this is meant as an input to climate policy negotiations, as well as to actions to actually address these emissions. And there are similar pieces of work that are basically taking satellite imagery, applying a couple of expert-driven labels to it, and then trying to kind of extrapolate that labeling to a broader set, a global level, in order to give us more on-the-ground information about quantities relevant to climate change. So these are things like, where's deforestation happening? Can we pinpoint that from satellite imagery? Where are the buildings that we have, and what are the types of those buildings, and what are the energy efficiency characteristics of those? What types of crops are being grown on different types of land, and what is the yield of those? These kinds of questions are questions where we ideally would have on-the-ground data or on-the-ground targeted surveys to give us this information at scale. But in places where we don't have it, kind of distilling this data from satellite imagery is one potential option. Another place AI is commonly used is to improve predictions. So the image on the slide is from a nonprofit called Open Climate Fix, which is working with the UK power system operator to improve their forecasts of electricity supply, like solar and wind power, as well as electricity demand. And the goal here is that by having more targeted and more accurate near-term forecasts of how much solar, wind, and demand are occurring on the power grid, this helps us to better balance and manage grids with large amounts of renewables, which is to say, it makes it possible to actually incorporate renewables and low carbon power into these power grids. And what they're doing in order to improve predictions here is they're taking in many different types of data, like historical data about how much solar power was produced, satellite or aerial imagery giving a sense of how much cloud cover is overhead the solar panels, and as well as the outputs of numerical weather prediction models, so physical models that are predicting something about the weather. AI and machine learning techniques can kind of find some nuanced and powerful correlations in that information in order to provide better forecasts. And in kind of using these techniques, this nonprofit Open Climate Fix, they were able to halve the error of the forecasts that were previously being used by National Grid ESO. In addition to just providing information, AI and machine learning is also used in various places to actually help with automated decision-making. For instance, the control of heating and cooling systems in buildings, in data centers, in industrial facilities, based on factors like what the weather is outside, what the footprint of a building maybe looks like, what the temperature and occupancy of the building actually look like. By kind of ingesting a bunch of sensor data that give insight on these different characteristics, AI and machine learning techniques can basically find patterns in this data that suggest better control strategies, and as a result, improve the efficiency of these systems. And the potential here is quite big in the sense that heating and cooling make up about half of the greenhouse gas emissions associated with buildings. And so improving the efficiency of these systems is a potentially very powerful lever. Similarly, on this thread of kind of making existing systems more efficient, another place that AI and machine learning are commonly used are for predictive maintenance. This basic idea that you can take, again, sensor information about something like your railway system in order to understand where there might be faults in various switches on the railway system or other equipment, and then use that to preemptively fix issues or fix them in real time. So Deutsche Bahn, the German rail operator, for example, uses AI across many different workflows to actually improve the efficiency and timeliness of their trains. Another similar example, not pictured on the slide, is this idea of detecting and fixing methane leaks in natural gas infrastructure as natural gas is transported from where it's extracted to where it's consumed for heating or electricity production. Methane can leak from these natural gas pipelines or from the compressor stations along that pathway. And so AI and machine learning have been used to both detect leaks where they are occurring, as well as, and as a result, allow them to be fixed, as well as maybe do anomaly detection on sensors that are outfitted on that infrastructure in order to understand if something might break. In addition to actually helping us manage and maintain real-world kind of on-the-ground deployed systems, AI and machine learning can also play a helping hand in accelerating scientific discovery. So things like helping us to create that better battery more quickly by analyzing the outcomes of past battery experiments and using that to suggest which batteries we may synthesize next. And this general idea of kind of helping us better search through scientific discovery spaces comes up across a lot of different areas outside of climate as well. But within the context of climate, it comes up, for example, in the discovery of better batteries, the discovery of better electrofuels, better solar PV panels, as well as better CO2 sorbents for carbon capture applications. Another place in science and engineering that AI can play a role is in helping to approximate time-intensive simulations. For instance, when you're running a climate model, a kind of physics-based climate model, these are really, really computationally intensive to run. And as a result, you're often only getting answers about kind of what is going to happen with the climate in the future at a resolution that takes, for example, the entirety of New England or a very hefty fraction of New England and gives you literally one data point for the entirety of New England. And this is tricky because actions to actually, do disaster response, you often need to have much more resolution at a city or town level. If you want to understand how wind patterns are going to change in the future in order to understand where to install wind turbines, you need to have much more granular insight. And so the coarseness of climate models is unfortunately not facilitating on the ground action in terms of, what do you actually do in a specific locality? And so AI and machine learning are being used in various ways to help with this, one of which is helping to approximate all or portions of climate models, things like clouds that are very kind of intensive to resolve the physics of, by learning surrogate models that are cheaper to run and can be potentially stuck back into the climate model. And other applications include downscaling, basically learning relationships between the very coarse outputs of climate models and more fine-grained information we have today, like weather, in order to then extrapolate those relationships into the future, and as a result, come up with more fine-grained climate predictions in the future. And then last but not least, we often think of AI and machine learning techniques in particular, kind of ingesting data in order to make decisions or to provide insights. But there are ways that AI and machine learning can actually help with data management itself. For instance, there are various federal kind of databases that capture information about electricity generation, and they have different, they may be referred to the same power generators, but those power generators are referred to by different entity IDs or names in those data sets. And so identifying which entries actually correspond to the same generator and automatically merging those is one place where AI is already starting to be used. Another application is in scenario generation, this idea that maybe you have some historical data capturing wind power generation, and you want to use a machine learning model to actually identify patterns and learn patterns in that historical wind power generation. And then based on that, you can potentially use that to generate future scenarios for different time series of wind power that may occur by looking at the distribution that was learned over your historical data, shifting the distribution parameters to be more reflective of what we're going to see in the future, and sampling from that distribution in order to actually get kind of representative wind power scenarios in the future. So this is kind of a high level and very quick overview of ways that AI can be used for climate action. And one thing I want to emphasize is that there's a real diversity of types of applications here. And there's a diversity as a result of actual requirements or on the ground realities in terms of what these applications look like. In particular, when we think about the dominant paradigm of AI and machine learning today, many techniques are often assuming big data, big compute. They're assuming that you can learn everything you need from data. And then they tend to optimize for a particular notion of performance, which is average accuracy across many different data points. But on the ground, as we look across these climate applications, we often have less data, or we might have a lot of data, but it might be hard to move. This is true, for example, on electric power systems, where you actually have tons and tons of sensor data that's collected. But communicating that data across the power infrastructure, communication is a bottleneck, storage is a bottleneck, and so you may not actually want to use all of that data. In some cases, you're dealing with much less compute due to kind of actual physical realities, like you need to do computation on an edge device on something like a power grid, or because of organizational realities like how much compute any given organization actually has access to or can pay for. And of course, there are energy and emissions implications to large compute, as we'll talk about soon. There are often many places where you have useful knowledge that can be leveraged on the ground from your climate-related tasks. So for example, for power grids, we know something about the physics of the power grids, and learning it again from scratch can be really data intensive, potentially unnecessarily so. And we often care about different metrics across these things. So instead of just average accuracy across all data points, maybe we care about performance on a specific set of data points. Maybe we care more about safety than raw accuracy. Maybe we care more about privacy or uncertainty quantification. And so we tend to see kind of a diverse set of metrics that come into play. And these lend themselves to a diverse set of techniques across physics-informed and safe and robust machine learning, which comes into play across areas as diverse as climate prediction, industrial optimization, and building optimization. Interpretable machine learning and uncertainty quantification, which have bearing across different policymaking, high-stakes contexts, early warning and emergency response contexts, and so forth. To different types of generalization. So ideas that models that are trained, for example, on kind of crops in one area to identify crop yields in one area. Maybe they can generalize to identifying crop yields in another area by using various additional spatiotemporal data in addition to literally just kind of raw satellite imagery, or this idea that often when you're doing things like biodiversity, you have kind of information about different species that have been collected. And you have many more observations about common species and many fewer observations about rare species. But what you actually care about is predicting something about rare species. So you care about generalizing to kind of a different distribution than your model was actually trained on. And also there are many angles where AI and machine learning are being used in the context of causality. So actually kind of going into climate physics related areas and trying to like identify which variables might be causing each other, which you can't do just from raw data, but you can do if you also have some physical process models that you're using in there. As well as various uses for energy efficient machine learning, tiny machine learning for small devices, and auto machine learning, where there have been kind of various studies that have shown that our existing techniques for auto ML, which is this process of actually constructing machine learning models kind of automatically and identifying which models are going to best perform, that they don't necessarily work that well on climate related tasks, but they've been very overfit maybe to other tasks like in computer vision and in natural language processing that we've cared about. So there are lots of different opportunities for innovation across many different types of machine learning techniques, not just in some sense the predominant paradigm of large foundation models. And so it's important, I think, as we think about where machine learning is useful and where we need to push different angles of innovation, that we think very specifically about this. To talk a little bit about my own work, my group's work focuses a lot on how do we actually develop AI and machine learning techniques that are well fit for some of the challenges that we face in electric power grids? So electric power grids make up about a quarter of global greenhouse gas emissions, and decarbonizing them is going to require integrating more time-varying renewables, integrating more distributed devices like flexible demand devices like electric vehicles that can actually flexibly shift when they're using power based on when renewable energy is available. And this is requiring us to actually manage power grids at greater speed and scale than we had before. But these kinds of changes on power grids are tricky because power grids are physical systems that you need to make sure to not break. When you put power into the power grid, the power flows along lines according to the physics of the power grid. You have various hard constraints you need to satisfy to make sure that you're not telling equipment to not do to do things it can't do, or to make sure that your power grid is staying stable. And layered on top of that are all sorts of decision-making processes that you're making all the time. Traditionally, these kinds of decision-making problems on power grids, how you actually schedule power, how you actually modulate different devices to maintain kind of voltage stability and frequency stability, these are done traditionally through optimization and control techniques where you explicitly write down the physics of the power grid and solve over them. And the nice thing about those techniques is that they satisfy many constraints, but they struggle with the speed and scale that we need in order to manage these very dynamic and fast-moving power grids. And so machine learning has been proposed as one approach that we can use here, which can, ingest a bunch of data and provide answers in a very fast and scalable way, but where unfortunately machine learning techniques in their native form really struggle to satisfy hard constraints, hard boundaries that you really can't cross. They often provide infeasible solutions, solutions that are not physically realistic. And so how do you bridge these two worlds? How do you get the benefits of AI and machine learning to provide fast and scalable optimization and control? But how do you do this in a way that still satisfies constraints in the same way that kind of your traditional optimization and control techniques would? And so what my group does is think about this in the context of specifically deep learning models, so this idea that you have a machine learning model that is taking in some input from your power grid and producing some output. And this model is a deep learning model, which is basically a bunch of functions composed together where the parameters of those functions are updated iteratively based on the performance of the model at a given moment. Well, if we have just a bunch of functions composed together, and we have knowledge from the power system that is encoded as functions that we care about, maybe we can actually write down those functions from power grids and embed them into the way we design deep learning models in the first place. So now we have deep learning models that are more data efficient because they don't have to relearn certain physics, or we have actual certain provable guarantees over some property of their output, the safety of the output, the robustness of the output, because we've actually engineered that into our deep learning system. And in our group's work, this plays out in many different ways, thinking about things like how do you create power grid forecasts that are cognizant of not making mistakes associated that are particularly bad for power grid scheduling. So how do you actually build knowledge of the scheduling algorithm into the forecasting algorithm so you don't make bad mistakes? We also use these kinds of techniques to learn fast and feasible approximations to power systems scheduling problems, where you have to schedule power on the power grid subject to a bunch of power grid physics, but you need to do this quickly while still satisfying the physics. And so we use machine learning techniques to actually approximate these power grid scheduling models, but in a way that we still preserve fidelity to the physical constraints, things like the power flow equations on power grids, by actually embedding the power flow equations into the neural network. And we also look at ways to do distributed control of devices like solar panels, like inverters, like batteries, using deep learning and using deep reinforcement learning, but in ways that still preserve kind of stability and fidelity to hard physical constraints by, again, embedding control theoretic information into the way that we design deep learning methods. So this is a super high level overview of ways that one might think about kind of designing machine learning methods differently based on kind of actual constraints or needs of the underlying system. But I hope it gives a sense basically of this idea that, machine learning is not kind of a monolithic, machine learning innovation is not a monolithic set of things. It really is that we need to think really carefully about what requirements and constraints we have on the ground and design machine learning techniques to be fit for purpose to those specific things. So I spent a lot of time talking about, where AI can be leveraged for climate action. But as I talked about right at the beginning, AI's relationship with climate is multifaceted and nuanced. And so I want to talk about the other aspects of this relationship. One is that AI itself is having an impact on climate through the direct, computational cycles that it requires, as well as the hardware underlying it. And so in particular, when we think about the impacts of AI on the direct impacts of AI on energy and climate, we break this into two categories, one of which is operational impacts. So impacts associated with the energy and the water that are consumed during doing actual computation. And we also want to think about the embodied emissions and materials impact. So given the hardware that these computations run on, what are the impacts that come from producing, transporting, and disposing this hardware? And the numbers here are a bit kind of contended, right? So some estimates would say that in 2020, the overall information and communication technology sector made up about less than 2% of global greenhouse gas emissions. Some small but unknown fraction of that was AI related, and it was unclear, but kind of most of it was operational, some of it was embodied. And these emissions came from the AI part specifically, came from different parts of the life cycle of an AI model. So when you create a machine learning model in particular, you develop the model, you figure out what, for example, neural network architecture makes the most sense. You do a lot of experiments to figure that out. That aspect of developing the model can take tons of energy, but it's done that process of model development is done more infrequently. Models are then trained upon a specific set of data, and that is a relatively energy intensive process, but it happens somewhat frequently, somewhat infrequently, somewhere in the middle. And once you have a trained machine learning model, you use it. And so this process of inference, each inference takes a smaller amount of energy per run than training or development, but you're often running the model much more frequently. So there are questions in different workflows of, do more emissions come from training or from inference? And one thing we're seeing is that even though I gave this picture of, less than 2% of greenhouse gas emissions in 2020, this electricity demand is rapidly growing. So this figure on the slide is a projection from the International Energy Agency, where they note, looking at a combination of historical and future data, that there's about a 2x increase in global electricity demand from data centers, AI, and crypto. So this is not just AI, this is a couple of things lumped together, but that we're anticipating a 2x increase between 2021 and 2026 in electricity demand from these three things. And while 2x maybe doesn't seem like a lot, if you contextualize this to historical estimates, so where we actually saw between, for example, 2010 and 2018, so this sort of preceding 9 years to that estimate, we saw only a 6% increase in electricity demand from data centers, AI, crypto in those years, despite the fact that compute instances increased by about 6 times. So what happened? Basically, in the past, even though we were starting to use much more compute, our hardware was keeping pace in the sense that hardware was becoming efficient at a similar rate to this increase in compute instances. But we're potentially in a very different regime now, where actually the amount of compute we're using is outpacing the speed at which hardware is becoming much more efficient. And so this is definitely worth keeping an eye on and definitely worth understanding what do we do about this challenge. The dynamics of where emissions are coming from are also changing. So in the past, we kind of see estimates from tech companies like this chart is from Facebook, where before, when they had kind of their standard recommendation models, the emissions that came from inference, so use, were actually dominating the emissions that came from use were actually dominating the emissions that came from training. So basically it didn't take that much to train a model, but then when you used it, it took, you used it so much that the emissions from inference were actually dominating. Or sorry, apologies, reverse. So in this chart, RM1 to RM5 are old recommender system models. And these are ones where they were seeing that the emissions from training were about equal to the emissions from inference. The newer model, the language model, they're often seeing that emissions from inference are actually dominating emissions from training. So it's actually more expensive to actually keep running the model and use it in real time than to actually train the model because of the number of times that's happening. We're also seeing that as there's this shift towards using more multi-purpose models, these multi-purpose models are each more expensive per inference than task-specific models. So this idea that before we were using smaller, more fit-for-purpose models, and so each time we were using those smaller fit-for-purpose models, the emissions associated with each use were smaller. But now we're using large multi-purpose models, often for those same tasks, and that's causing each inference to become much more expensive, which has implications for the fact that if we're using models more and the models we're using are more expensive, then actually that has huge implications for inference-related emissions going up. So understanding these dynamics and trends is super important and can kind of yield different pathways forward in terms of how we actually reduce emissions and kind of where it's the most important to reduce emissions. And as a result, transparency from data center, from tech companies, from data providers and so forth becomes very important in actually figuring out what to do. One argument people will often make is, okay, but fine, so you see electricity usage going up from AI-related workloads. This isn't a big deal because you can just green the grid and install renewables. This is important to kind of green the grid, decarbonize the grid in order to make sure that all of our electricity usage is using less emissions, but it's insufficient. So one big idea is that all of our pathways to actually hit greenhouse gas emissions reduction targets rely on us actually improving the efficiency of energy usage, not growing total energy usage, but actually making everything much more efficient and using less. And so in addition to greening the grid, we also have to think about the fact that objective load increases when it comes to electricity usage are not necessarily consistent with climate goals. In addition, kind of emissions are not the only thing we care about. Kind of increased electricity, increased AI usage and increased data center siting has caused things like increased usage of water for cooling in data centers. And often this comes from public water supply in places with lots of water stress. And of course, there are huge materiality and resource impacts associated with the underlying hardware. So it's important to think about this issue holistically in terms of what can we do to actually objectively bring down usage in addition to greening the electricity behind all of that. All right, so that was a kind of a deeper dive into this idea of, okay, so AI itself has direct impacts on climate from computation and hardware. But I started the talk by saying, AI and climate, the relationship is not just AI can be used for good things and AI itself has a direct footprint, but it's also that AI can be used for bad things, for things that unfortunately actually counteract climate goals. For instance, AI is pretty widely used to accelerate emissions-intensive industries, for example, oil and gas. It's used to, for example, accelerate the process of exploration for new kind of fossil fuel reserves, as well as to improve and make more productive and cheaper the extraction of fossil fuel related resources. And some kind of various reports have looked at this and found that, AI has boosted production levels by, several percent in many cases, and could generate, hundreds of billions of dollars of value and for the oil and gas sector by 2025. And so we're looking at a case where when we're trying to make kind of green energy, right, more competitive against fossil fuels, there unfortunately is a lot of resource going into using AI to make fossil fuels more competitive. Another example in agriculture is the idea that AI is being used as part of the quote unquote Internet of Cows to manage livestock at scale in ways that unfortunately can entrench the role of methane producing agriculture. So bovine agriculture, cows, for example, is a huge source of methane emissions, and kind of entrenching that or accelerating that can potentially, unfortunately, keep that methane emissions production around. Last but not least, there are various ways that AI is used for applications that we don't often think of as linked to climate change, but potentially have pretty big climate-related implications. So, for example, AI is a key driver, no pun intended, behind autonomous vehicle technologies. And autonomous vehicles could be good or bad for the climate. There have been various studies that have looked at this idea that there are ways that autonomous vehicles can potentially improve the efficiency of driving by fostering eco-driving, by doing things like platooning, where different cars are able to kind of ride in the kind of wake of another car in order to improve the efficiency of the actual driving. But that kind of autonomous vehicles might lock us into privatized, energy-intensive transportation, and also increase the amount that we actually drive, and that these might actually counterbalance the efficiency gains that we get in the first place. So AI and machine learning as being, key technology behind autonomous driving, we want to think about, well, are there ways that we can shift this? If we are using AI to support public multimodal transportation and low carbon transportation, that's a very different pathway than if we're using it to promote high carbon privatized transportation. And so we have some choices that we can make here in terms of which pathway we go down. AI is also a big driver behind increased societal consumption. So things like targeted advertising and on-demand delivery in ways that, debatably, right, they may or may not improve happiness depending on the particular applications we look at, but do increase consumption and emissions as a result. AI changes how we consume information online, contributing to both good information. There are lots of applications that try to better target information towards people in order to help them make more targeted decisions about climate-related things, like, what kinds of energy efficiency retrofits should they do in their particular house. But unfortunately, AI is also driving misinformation and polarization online through kind of content personalization and through amplification of certain of clicks, or of amplifying often incendiary content in order to kind of promote clicks and engagement in ways that have implications for how people actually relate to climate change topics, or to how healthy of dialogue people are able to have on these topics. And AI is also inducing various power shifts in society due to kind of who has access to these technologies and who is developing them. Often AI technologies are developed by, a small set of entities, often coming, for example, from the global north. And yet climate change related solutions, for example, are often needing to happen, again, globally, with kind of various nuances and differences at how this pans out at different local scales. And so having a small set of entities that are controlling this development of technology can also then cause those small set of entities to shape the narrative of those societal solutions, and that's not necessarily a great thing. So given this multifaceted relationship between AI and climate change, what can we do? I'd say that I'm gonna address really quickly maybe potential types of action that two different sets of communities can take, and that's the AI community and the policy community. On the AI side, what I would say is that even though there has tended to be a bit of a bias towards let's all work on let's all go all in when it comes to AI innovation on these specific types of large models that get a lot of attention in the news. As I kind of tried to argue earlier, the kinds of innovations that are going to benefit different climate change related applications on the ground require a relatively heterogeneous set of methods that are tailored to fit different kinds of assumptions with respect to how much data we actually have, how much compute we actually have, how much knowledge we already have, or different metrics we care about. And so it's important that there continues to be a diversity of methods that are innovated on, both within the context of climate change applications specifically, but also more broadly. To that point, I think there are lots of important things to think about in terms of what applications we work on and how, both, ideally, are you working on climate change related applications? That would be great. But also, if you're working on an application that might not kind of at first glance seem related to climate, like autonomous vehicles or like targeted advertising, really thinking through, are there ways that you can shift how you work on that to be more climate aligned? So for autonomous vehicles, for example, can you actually support public and multimodal transit by kind of in the kinds of data sets you think about and in the kinds of innovation you're fostering, rather than necessarily kind of consumptive private transit? There are various practices that can be taken at the individual and organizational levels, from things like reducing wasteful training runs in machine learning models, all the way to doing things like setting internal carbon pricing within an organization to enable more climate aligned practices. And a big one I'd say is public communication. I'd say that right now there's so much hype around AI, and in spheres like climate, where people are desperate to take action, there's a big search for solutions, but also a huge opportunity cost if we waste time and kind of go down paths that don't make sense. And so for those working on AI, it's really important to communicate publicly about these techniques in a way that is appropriately humble about what they can do, and what they're well suited for, but also what they're not well suited for, what some of their limitations and assumptions are, and what some of their risks are, so that communities like the climate community can actually take that information properly into account when figuring out what to do. On the kind of macro kind of policy side, for example, there are also lots of actions that can be taken to both foster the use of AI for climate action where it makes sense, as well as to kind of bring down the negative implications of AI for climate, both through its direct impacts and its negative implications, negative applications. And so on the first front, there are lots of levers in terms of, for example, establishing better data and digital infrastructure to make sure that that data is representing different climate change related use cases across different geographies, and that compute is accessible to those entities that need it. Various levers in terms of better targeting research and innovation funding in order to actually fund the kind of heterogeneity of approaches and heterogeneity of people who actually need to make those approaches go forward, as well as investing in better deployment and systems integration. So things like on electric power grids, how do we kind of make sure that we're able to develop AI and machine learning techniques in a way that's appropriately cognizant of the fact that these are kind of physical safety critical systems, without breaking those systems in the first place by having the right simulation infrastructure and metrics around. And then in addition to, of course, fostering AI for climate action, how do we bring down the negative impacts of AI? And that involves a combination of more transparency and reporting on direct impact, so that we can better target where those are coming from and take better actions to actually shape them. And again, some of these trends are nuanced, like the relationship between training and inference related emissions, where the action you take is different based on what that emissions balance looks like. And then also kind of embedding climate as a core consideration within AI strategies. Right now, as different countries and kind of states or subnational entities kind of put forward AI related strategies, they often think about, well, we need to make sure that the AI that is put forward is responsible, is equitable, is privacy preserving, is not biased. And I think similarly, the idea that the AI we put forward should be aligned with climate goals, both in terms of its direct impacts and its applications, also needs to be kind of a critical aspect how we think about doing responsible AI. So for those who are interested in thinking more about some of these issues, both on kind of how you can leverage AI for climate action, and also how you can kind of mitigate some of AI's negative impacts, I would encourage you to kind of join the community of people who are thinking about this. So in particular, I'm a co-founder of a nonprofit called Climate Change AI, which really tries to bring together the innovation community, practitioners, and decision makers who care about this, and provide a combination of educational resources, provide opportunities like workshops where you can actually share the work you're doing and kind of build collaborations with others, funding to kind of help kickstart various collaborations and projects, and various other kind of ways to both kind of meet people who are working in this area, to share what you're doing, to get resources for it, and to also learn more about this space. So I definitely encourage you to join in. And with that, I would say, to close, again, AI is something that has, gained a lot of attention in our society for better and for worse. And I really hope that the way we actually move forward on kind of innovating and deploying AI can actually be in service of climate change related goals. And I think that can definitely happen if we think properly holistically about what AI means for climate action, and kind of take actions to actually align those different vectors through which AI is affecting climate change with actual climate goals. So thank you so much, and I look forward to any questions.
Priya, thank you so much for that. Just for the folks who were joined a little bit later and didn't hear me, I'm Lara Hesse-Fischer. I'm the host of MIT's Climate Change podcast, and I'm going to be moderating our Q&A. That was a whirlwind tour of AI and its use for climate change. And it's not often that you get that kind of detail as well as a practical call for action. And I know that's what a lot of people on the call today is really looking for is, okay, I learned about this stuff. I don't want to just know about it. I want to know how I can use it, how I can think about it, how I can talk about it to the people inside of my networks. We have a lot of questions from people spanning a lot of different kinds of topics. We have people who are asking about how AI is helping us understand how the earth is changing. We have questions about what's most exciting for you. I want to start us off with a couple of questions that have come in with concerns about the use of AI regarding climate change in particular. So let me read the three questions, and then I'm going to put a little bit of a point on it. So one is, how can we ensure that AI research and development continue to prioritize addressing climate change? How can we ensure that AI technologies are developed and deployed in a way that benefits everybody, not just the wealthy? You were talking about that as well. What are the ethical implications of using AI for climate solutions, especially in terms of data privacy and equity? And those are huge questions. So my real question for you is, what's being taught at MIT about this stuff, right? How do you teach students and graduate students about AI and climate, AI and equity, AI and data privacy, and how does that translate that into what's talked about in conferences and communities of folks that are working on this technology?
Absolutely. So there's a lot in there to unpack. And what I would say is that the kind of pedagogy on AI and climate and their intersection at MIT is nascent, but kind of in the last 2 to 3 years, there's been a big focus on hiring faculty who work at the intersection of AI and climate, and where we are super, super excited to bring these conversations into play. And so to really teach people when they're doing AI and machine learning and coming from that side, that AI, like really doing AI and machine learning well in ways that benefit climate action, means really understanding the needs of the climate change related problems on the ground and developing methods in a way that services that. And that's not just some abstract notion of oh, there's a problem. It has, like I talked about power systems, it has certain safety attributes, but who are the people on the other side of that who would actually be leveraging these techniques, whose problems you're purportedly solving? What are the actual problems they're facing? How do you actually engage with them? So really enabling this participatory design angle. More broadly, I think that kind of to get at a couple of the points in the questions there, I think that in order to ensure that AI is developed in a way that actually fosters climate action, and then in a way that really not just kind of benefits in a trickle down way, but is really like fundamentally addressing the challenges of people all around the world and is not just concentrating power. I think it requires two big things. One, we have to be much more nuanced about the way we actually talk about AI or let people talk about AI. I think often there's a common narrative among technology solutions providers of things like, we should be allowed to continue to develop AI in the way we want to, and have it, for example, consume as much resource as we want to, because it's going to be helpful for things like climate change. But if you really dig down into that, the types of AI that are being used for climate action are often different from the types of AI that are being promoted through those arguments. So we really have to, I think, get much more nuanced about when we say we want to promote AI because it can be used for climate action. What type of AI? Is the way that AI is done the same as how kind of the mainstream of AI is done? And how do we more cleverly route our funding streams and our other incentive structures in order to actually address head on some of the challenges that are actually going to be helpful for societal applications, rather than things that in the abstract could down the road be helpful for societal applications. Yeah, so and I'd say that this kind of idea of also often entities that could benefit from climate change related solutions are not the ones with deep pockets. And so I think becomes really important for the role of philanthropy, of government, and of kind of corporate giving to really make sure that money is going to addressing challenges that are faced not just by people who have the money.
Yeah, I appreciate your comments about participatory design and how once there's that human to human interaction, that really helps not only creating solutions that are going to be applicable and really used, but then also, yeah, there's that human element. Like these are real people who are using these tools. How do we design for them and with communities like them in mind? Are you collaborating with different parts of MIT? Or are you looking to collaborate with different parts of MIT that are really focused on that community engagement and real world engagement? I'm thinking also there's the MIT Climate Project that President Sally Kornbluth launched last year. That's really kicking off now. That's focused on not just doing independent research, but really that impact on the ground. Can you tell us a little about how that's manifesting?
Yeah, so in my work specifically, the kind of key set of stakeholders that I tend to collaborate with is power grid operators, who are the ones who are actually figuring out how to schedule power. They are then beholden in turn to regulators who are making sure that they're managing the power grid in a kind of low cost and reliable way, in a way that's consistent with decarbonization goals. And so a lot of my engagement ends up being in those two streams, with power grid operators and with regulators. And I would say that in the context of MIT, I think there's some really great like partnership building related initiatives that are coming into play because of things like the Climate Project, because of things like the MIT Energy Initiative, that I think are really, really beneficial. Outside the context of my work, I think there are entities like the Environmental Solutions Initiative that are really looking at participatory design for technology solutions, including AI solutions that are affecting really marginalized communities in this context. And so I think there's just a ton of really great kind of infrastructure and kind of intellectual interest across many different kind of people and organizations at MIT.
I know the folks that are working at the Environmental Solutions Initiative, and what's happening is that you have researchers who are from these countries around the world who are coming to MIT, working with MIT faculty, and then translating that into work that they're returning back to their countries on these kinds of technologies. That goes into another question that came up. You mentioned opportunity costs. As we all know, we got to move fast on this whole climate thing. We don't want to waste our time on things that are not important. Can you talk about what kinds of collaborations are happening between AI researchers to advance this kind of research, but then really practical solutions on the ground so that we don't waste time on things that are not, don't matter, or that are kind of recreating other mistakes or dead ends?
Yeah, so I would say that these kind of opportunities for exchange between different people who are doing what I think has like relatively recently been coined as application driven innovation in machine learning. So innovation that is really contending with the requirements of on the ground applications like those in climate, and really then surfacing those to strengthen how we develop AI methods in the first place. I think there are various venues that's happening. For example, at the major machine learning conferences, there are workshops that people will propose to hold, focused on different, areas of this. So our nonprofit Climate Change AI, we hold a series of workshops focused on AI for climate action. There's also a series, for example, on AI for health. There have historically been things on AI for disaster response, for example. And I think these kind of practice informed innovation communities are really critical, because often when we're working with on the ground problems, we're facing a shared set of challenges, and kind of exchange on how kind of we move forward on our methodologies and in our partnership building in order to actually address those on the ground challenges, I think is critical. So these kinds of workshop style venues have been, I think, really crucial.
Yeah. Okay. That sounds great. I'm wondering if we could zoom out for a moment and help us understood what could happen versus what is happening right now. So could you just give us a sense of like, where are we on this technological adoption curve or the deployment of AI for climate benefit? You gave us a read into the work that you're doing, but of course you also gave us 7 different themes with like the dozen applications inside of each theme. What's a way for the people who are paying attention to the conversation today to kind of get their head around where we are as a society regarding using AI for climate?
Yeah, so I'd say that applications of AI that are providing some kind of insight that helps a decision maker are pretty widespread. So this category of using satellite imagery in order to figure out where the crops are, this is something that NASA Harvest and Surveyor and other kind of public entities that are actually working with, right, like farmers to figure out what to do. Like they are using these kinds of techniques. Um, I think the pitfall that can often happen with kind of applications that are take satellite imagery and provide insight is that that insight needs to actually serve some decision maker in making a decision. Kind of providing insight in and of itself isn't a climate solution. And so I think they're kind of just making sure that the way those applications are developed is actually done with a decision maker in the loop to understand what it would take for them to actually use those insights becomes really critical. But I would say that these kinds of applications are moving forward quite broadly. Um, and certain kind of optimization applications like AI for improving energy efficiency in buildings are also kind of fairly widely deployed, because you have kind of great conditions of you have sensors and other automation technologies that are already being deployed that you can actually put AI solutions on. And then often these are things where, because you're making things more efficient, you're often reducing cost associated with things like energy usage, and so there's a big societal incentive to actually help those applications move forward. So those are some ones that I think are happening on the ground right now.
So we're getting up on our last couple of questions. So I'm going to ask you a question and hope that you can answer it with one example, and then we'll move on to our final question. The question is, there are a number of people who are asking about how do we understand, how can AI help us how the Earth is changing? So, for example, the albedo effect, right? How the dynamics of melting ice sheets, et cetera, are changing that. Deforestation, loss of grassland, the permafrost felting, again, related to not only the albedo effect, but also methane emissions from that. Is there like a cool example or something that you've heard that's like particularly interesting about how AI is being used for something very specifically regarding that kind of monitoring?
It's a great question. I mean, so AI is definitely being used for things like understanding where methane emissions are coming from in terms of natural sources. So, for example, things like um, sensing methane emissions in the Permian Basin and figuring out that actually the estimates of methane emissions there have been underestimates in the past of what's actually happening. And that requires basically cleverly using different types of satellite imagery in order that actually contain information about methane emissions in order to actually get those estimates. So that's one kind of targeted example.
And that's so important. As a lot of people on the call know, reducing methane is one of the fastest ways we can reduce our carbon impact in the short term. So let me ask you our last question. I'm so sorry that our time is ending with you, because I bet a lot of the people on the phone on the call have lots and lots of more questions. They'd love to spend an hour more with you. But tell us, what excites you the most about the potential and the future of this technology as it relates to climate solutions?
Yeah, so I think what excites me the most is that fundamentally, a lot of AI and machine learning techniques are able to be picked up and used by a lot of different people. There's a huge open source culture within AI, a lot of libraries that people can pick up and actually just start kind of get started. And that's not something to be taken for granted. So I think that if we really put forward efforts to educate more people about AI, kind of how to use it, where it's useful, what it means to do it responsibly, I think there's really an opportunity to sort of unlock innovation and potential from across society, including kind of ground up efforts from people who actually, are owners of the problems we're trying to solve.
Oh my gosh, thank you so much for those inspiring final remarks. I just want to thank you, Professor Priya Donti, for sharing your research, your insights, and your excitement, your passion for this technology and this application. Thank you to everybody on the call for joining us today. Thank you for the MIT Alumni Association for organizing this program, for the team that worked really hard on putting it together. And all of you, no matter when you graduated from MIT or your affiliation with MIT or what you're doing now, you're here and you joined us today because this issue matters to you and you're trying to increase your understanding and application of this. So just I really appreciate you taking the time to move your insights into action. Thank you so much for having me, and have a great rest of your day.